Good day everyone and welcome to our next lesson. In this video, we will be talking about electrochemistry, which discusses the involvement of electricity in chemical reactions along with its applications. So let's begin. For a brief overview, coming from the term electrochemistry, it seems that it's a combination of two terms. No? In fact, it's a combination of electricity and chemistry because we are figuring out the role of electricity in chemical reactions. The most popular applications of electrochemistry include batteries because we use batteries in all of our everyday lives. We have batteries in our gadgets, we have batteries in our automobiles, and we also have big batteries in our electricity production facilities because we need a way on how we can store electrical energy before we need to use it. Okay, so expect in our later discussions that we will be heavily focusing on batteries. The core of the discussion of electrochemistry revolves around mastering the redox reactions. Redox reaction mean reduction and oxidation reactions. So these two half reactions always exist in one complete redox reaction. You cannot have one without the other, and you cannot have two reduction reactions nor two oxidation reactions. Okay, so they always have to be paired as reduction and oxidation. I have here some mnemonics to guide you on when to decide if a reaction is a reduction reaction or an oxidation reaction. First, for reduction, we have GEROA. GEROA stands for gain of electrons, means reduction, and that is the oxidizing agent. And for oxidation, we have LEORA, or loss of electrons is oxidation, and that is the reducing agent. Based on those mnemonics, you can imply that there is an exchange of electrons in redox reactions. One half reaction, that is the oxidation half reaction, loses its electron, and the reaction that is lost is being transferred to the reduction reaction, which gains back the electron. In a way, it's just a transfer of electrons between two half reactions. Let's discuss these concepts further. Reduction and oxidation reactions always happen in pairs, as I have mentioned earlier. And we have to review how to determine the charges of elements in a compound or ion because these are very important in redox reactions, particularly in the balancing of redox reactions. Okay, let's have this first example. HCl plus NaOH yields NaCl plus H2O. We want to determine the oxidation state of each element on this equation. And for that, you will be needing a periodic table of elements. Here is our periodic table of elements. Now, the key to determining the oxidation state of an element is to first determine what group does it belong. So here are the group numbers at the top here. You have the group 1 elements, hydrogen, lithium, sodium, potassium, etc. Group 2 elements here. You have the transition metals from groups 3 to 12. We have group 13 here, which we also call group 3A elements. Group 4A, 5A, 6A, 7A, and then group 8. Now, what is the importance of these group numbers of the elements? From the group numbers, along with some guidelines, we can easily determine the prevailing oxidation states of the elements. Let's say, for example, aluminum. Aluminum lies in group 3A, therefore its oxidation state is positive 3. Why is it positive 3? Because aluminum is a metal. Now, just a quick review. An easy way to tell which are metals and non-metals in the periodic table is you simply follow this ladder: boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. Those elements that I have mentioned are what we call the metalloids or the semi-metals, and everything to the left of these metalloids are all metals except hydrogen, and then everything to the right of the metalloids are all non-metals. The significance of that is the metals would likely have a positive charge, while the non-metals would predominantly have a negative charge with some exemptions. For example, hydrogen can possess both a positive or a negative charge depending on its use. Okay, so let's use this knowledge to determine the oxidation states of the elements in our example. In this chemical equation, we have 4 elements, that is hydrogen, chlorine, sodium, and oxygen. Now, these 4 elements are what we need to find for their oxidation states in both the reactants and the product, because the change in oxidation states between the reactant and the product would signal that this is a redox reaction. Okay, let's start with HCl. For HCl, we know that this is an ionic compound because it's a marriage between a cation and an anion. The cation in this case is hydrogen. If I split this in two, so hydrogen being our cation possesses a positive charge. And from our periodic table, hydrogen is a group 1 element, therefore it possesses a charge of positive 1. Okay? That is how we determine its oxidation states. Now remember that hydrogen can possess both a positive and a negative charge. If it is used as a cation, hydrogen possesses a positive charge, while if it's used as an anion, it will have a negative charge. Okay? Next, we have chlorine. The chlorine in HCl is an anion, meaning it would possess a negative charge. Now, chlorine is part of group 7, which we also call the halogens. And all of the halogens, that is fluorine, chlorine, bromine, and iodine, if they are used as an anion, their charge is negative 1. If you take a look at HCl, if you add all of the charges, you would get a net charge of 0, which is to be expected if you have a neutral compound. Okay? Always remember that for all neutral compounds, the summation of all charges of all the elements should be 0. Okay, let's move on to sodium hydroxide. For sodium hydroxide, this is another ionic compound. Therefore, we can split this into its anion and cation. In this case, sodium is our cation, and then OH, or what we call the hydroxide, is our anion. Sodium, being a group 1 element also, has a charge of positive 1 in this case. Now, how about hydroxide? If I isolate hydroxide here, we write hydroxide as OH negative 1. The negative charge here pertains to the entire hydroxide ion, meaning if I add the charges of oxygen and hydrogen here, the sum of that should be negative 1. Now, always remember this, that for hydroxide, hydrogen is positive 1 still. How about oxygen? Oxygen is part of group 6A in the periodic table, and for elements in the group 6A, if they are used as an anion, their charge is negative 2. Always remember that. This applies to oxygen, sulfur, and selenium. If you take a look at our hydroxide ion, if I add negative 2 and positive 1, we would get negative 1. Negative 1 is the overall charge of our hydroxide ion. Therefore, let's now write that oxygen in sodium hydroxide has a negative 2 charge, while the hydrogen has a positive 1 charge. If you take a look at sodium hydroxide, the net charge of sodium hydroxide is 0. So if I add positive 1, negative 2, and positive 1, I should get 0. And that's the case. Okay? So sodium hydroxide is another neutral compound. Next, on the product side, we have sodium chloride. If I split this again to show the cation and the anion, our cation is sodium. Sodium being in the first group of the periodic table, it has a charge of positive 1. And chlorine being in group 7, it's a halogen, it has a charge of negative 1. Now, water is one of the most common compounds that you will encounter in electrochemistry. So might as well remember that for water, hydrogen has a charge of positive 1 and oxygen still has a charge of negative 2. If you take the summation of charges for water, that is 2 times positive 1 minus 2, that's equal to 0. All of the compounds we have here are neutral compounds, so the summation of their charges should always be equal to 0. Now, here comes the fun part. We can now determine if this reaction is redox or not. It will be a redox reaction if 2 elements change their oxidation states from the reactant to the product side. Okay, so let's examine each element. First is hydrogen. Hydrogen has a charge of positive 1 in the reactants. In the products, its charge is still positive 1. Next is chlorine. Its charge is the same in the reactant and the product side at negative 1. Next, sodium, both positive 1. And lastly, oxygen. In the reactant and the product side, it both has a charge of negative 2. So there has been no change in the oxidation states of any elements. Therefore, we say that this is not a redox reaction. Okay? It's very important for you to master the skill of identifying redox reactions. Let's have the next example. We have hydrogen or H2 plus oxygen or O2 yields H2O. Okay, for this next example, let's start with the products because our product is water, and as I have mentioned, water will pop up in most of our redox reactions. Now, you know that the hydrogen in water has a charge of positive 1 and the oxygen has a charge of negative 2. Now, let's determine the oxidation states of your reactants. This is another rule that you have to remember. if you find a free element in either your reactants or your products, all free elements have an oxidation state of 0. Okay? Regardless of their group number, if it is a free element, automatically its oxidation state is 0. So hydrogen, being a free element, has an oxidation state of 0, and oxygen, being another free element, has an oxidation state of 0. Now, if you take a look at hydrogen, on the reactant side, its oxidation state is 0, and on the product side, its oxidation state is positive 1. And for oxygen, its oxidation state decreased from 0 to negative 2. That means that this reaction is a redox reaction. Okay? Now that we know that this is a redox reaction, the next step for us is to determine what is the reduction half reaction and what is the oxidation half reaction. And for that, we simply have to divide this equation. Let's start with hydrogen. So we write H2 with an oxidation state of 0 yields H2O. If you will notice, I only isolated all of the terms containing hydrogen. So in the reactant side, only H2 contains hydrogen, and on the product side, water contains hydrogen. That is our first half reaction. For our second half reaction, let's now consider oxygen. On the reactant side, you have O2 with a charge of 0, and on the product side, water still contains oxygen. But the oxygen there contains a charge of negative 2. Okay? Now let's determine which among this is the reduction and which among is the oxidation. Let me remind you again of our mnemonics. Let's start with GEROA. Again, what does GEROA stand for? The gain of electrons means reduction. The gaining of electrons means that your oxidation state would decrease, because if you gain an electron, you become more negative. So if you take a look at our two half reactions, which among the two elements gained electrons? If you take a look at hydrogen, its oxidation state increased from 0 to positive 1. It became more positive. So that is not gaining of electrons, because we are looking for something that's becoming more negative, and that is oxygen. From an oxidation state of 0 in the reactants, it became negative 2 in the products, meaning it gained an electron. That's why it became more negative. Okay? So we say that O2 yields H2O is our reduction equation, or our reduction half reaction. That makes our first equation our oxidation reaction, because again, oxidation and reduction reactions always happen in tandems. And if we take a look at our mnemonic for the oxidation, that is LEORA. This is the loss of electrons means oxidation. So if you are losing electrons, you are becoming more positive, and that's what happens to hydrogen. From an oxidation state of 0, it became positive 1. So it lost 1 electron. Okay? That is how we identify which among the half reactions are oxidation and reduction. Now let's determine what is the oxidizing agent and the reducing agent. If you go back to GEROA, the gain of electrons is reduction, and that is the oxidizing agent. Our second equation is our reduction reaction. Therefore, oxygen in the reactants is our oxidizing agent. And for LEORA, oxidation points us to the reducing agent, and hydrogen is our reactant here. So therefore, H2 is our reducing agent. Okay? That is how we identify the oxidizing and reducing agents. Always remember that the oxidizing agent is part of the reduction reaction, and the reducing agent is part of the oxidation reaction. Okay? Let's take a look at the next example. We have magnesium plus 2HCl yields MgCl2 plus H2. Let's now determine the oxidation states of the elements. First is magnesium. It's a free element, therefore automatically its oxidation state is 0. There's another free element in this equation, and that is hydrogen on the product side, so that gets 0 as well. Next, we have HCl. From our previous example, we know that hydrogen here is a cation, meaning its charge is positive 1, and chlorine is an anion, its charge is negative 1. Now, how about for MgCl2? Magnesium chloride, or MgCl2, is an ionic compound. Therefore, if we split this into the cation and the anion, we can determine its oxidation states. Magnesium is part of group 2 elements, therefore its charge is positive 2. That is in the same way that group 1 elements have a charge of positive 1. Okay? So magnesium gets positive 2. And then chlorine here is an anion, therefore it still has a charge of -1. Now we have finished determining the oxidation states of all of the elements. Let's take a look if this is a redox reaction. If you take a look at magnesium, magnesium goes from 0 in the reactants to +2 in the product. There's a change in oxidation states, therefore automatically this is a redox reaction. Now let's determine the half reaction. So of course, the first of that would be magnesium. Magnesium, it's 0 on the reactant side, and on the product side, the only term with magnesium is MgCl2. So from 0, it increased to +2. Now, what is the next element that changed its oxidation state? Chlorine did not change its oxidation state. It's both -1 in the reactants and in the product, so we have hydrogen instead. On the reactant side, the compound with hydrogen is HCl, and on the product side, the term with hydrogen is H2. So in the reactant side, hydrogen is +1. On the product side, hydrogen is 0. Now, at this point, do not worry about not having to place the coefficients from the balanced equation. That's because that is not the right approach to balancing redox reactions, okay? So balancing redox reactions will be discussed later. But for now, let us select which among this is the reduction and which is the oxidation. Again, reduction is the gain of electrons. So which among these two equations displayed a gain of electrons, or which among the elements became more negative? So if you take a look at magnesium, from 0 it became +2, so it became more positive, while for hydrogen, from +1 it decreased to 0. So the decrease in the oxidation state signals reduction. Therefore, our second equation is our reduction equation. That makes our first equation as the oxidation equation, and oxidation manifests as an increase in oxidation state. That happens to magnesium. From 0 it became +2. Okay, and then oxidation is partnered with the reducing agent. Therefore, magnesium is the reducing agent and HCl is our oxidizing agent. Okay, this is one of the important skills that you have to master in electrochemistry. It's the identification of the oxidation and reduction half reactions and the identification of the reducing and oxidizing agents. The next skill that you have to master is the balancing of redox reactions. But before that, let's solve more examples so that you will be familiarized on how to determine the oxidation states of elements. Let's have number 1. We have zinc plus copper sulfate yields zinc sulfate plus copper. First, we have two free elements here, that is zinc and copper, so automatically they get 0 as their oxidation states. Now, if you take a look at copper sulfate or CuSO4, this is another ionic compound which we can separate its cation and its anion. Its cation is copper and its anion is sulfate. Now, the problem with copper is that it's part of what we call the transition metals. If you take a look at the periodic table, the transition metals are all of this colored red, and the problem with transition metals is they can possess several different oxidation states. For example, copper can possess either +1 or +2. Iron can possess either +2 or +3. Manganese can possess a lot of different oxidation states such as +2, +5, and +7. So you get the gist, no? All of these transition metal elements could have more than one oxidation states. Now, how do we determine which among the possible oxidation states is displayed in our equation? This is where your knowledge of the crisscross would come in. So let's go back. For this, we have to separate the cation and the anion. So our cation is copper. We don't know its charge yet. And then our anion is sulfate, SO4. But from our previous knowledge, we know that sulfate is an anion with a charge of -2. Now remember that this -2 charge is an overall charge for the sulfate ion and not just for the oxygen. Okay? The -2 applies for the entire sulfate ion. Now from this data, how do we determine the oxidation state of copper? If you know the principle of the crisscross, the numerical charge of the sulfate ion would become the multiplier of copper in the final form of the compound, and the charge of the copper ion, let's call it Y, would become the multiplier of sulfates in the final form of the compounds. So if we perform the crisscross, it would look like this. This would become Cu2, and then SO4, and then Y. If you take a look at this form of the copper sulfate and then compare it with our finished product, CuSO4, you would soon realize that the value of Y in this case should be equal to 2. Why is that? That's because if we write Cu2 SO4 2. And if we simplify, this becomes CuSO4. This is the same as our initial compound copper sulfate. Therefore, the charge of copper is positive 2. We know that the value is 2 coming from the crisscross, but we also know that it's positive because it's a cation ion. Okay? So copper here is positive 2. Next, we have the sulfur in sulfates. Now, we don't know the charge of sulfur here yet because we're not familiar with sulfur. So let's first go to oxygen. We all know that oxygen almost always have a charge of negative 2, except in some rare instances, no? So in this case, we know the charge of copper to be positive 2. We know the charge of oxygen to be negative 2, but we don't know the charge of sulfur. This is where we will be applying algebra. You simply let the charge of sulfur to become x, and then we need to solve for the value of x. Okay? If you will remember earlier, I have mentioned that for neutral compounds, if you take the summation of the charges of all the elements, that should be equal to 0. So that is what we are going to do in order to solve for the value of x. So copper, you only have one atom of copper, so that is 2. Plus sulfur, you only have one atom, that is plus x. Plus, for oxygen, we have 4 atoms, so that should be 4 multiplied by negative 2, the charge of oxygen. And this summation is equal to 0. From this equation, we can easily solve for the value of x. So x in this case is positive 6. Okay? Therefore, we now know that the charge of sulfur in copper sulfate is positive 6. That is how we determine the charge of the middle elements. Okay, let's proceed. On the product side, first we have zinc sulfate. And you have to remember this, that zinc, even though it's part of the transition metals, zinc almost always contains a charge of positive 2. If you will compare zinc sulfate with copper sulfate, copper and zinc both have positive 2 charges. So sulfur here would also have positive 6 based on our previous calculations, and oxygen has a charge of negative 2. And we have completed the oxidation states of this equation. Now the question is this a redox reaction? The answer is yes, because first, zinc changed its oxidation state from 0 to positive 2, and then copper also changed its oxidation state from positive 2 to 0. This is a redox reaction. Next, we identify what is the oxidation and reduction half reactions. Let's start with zinc. We have zinc yields zinc sulfate. From 0, it became positive 2. And then next, we have copper sulfate yields copper. From positive 2, it became 0. Which among this is the reduction reaction? Remember, the reduction reaction is where the oxidation state becomes more negative, or the oxidation state decreases. Therefore, that is our second half reaction. From positive 2, it decreased to 0. This is our reduction. And of course, the first one is our oxidation half reaction. What is the oxidizing agent? That is copper sulfate. What is the reducing agent? That is zinc. Okay? You have to be familiar with some of the tricks regarding the determination of oxidation states of certain elements. Because while we may have some general rules regarding the oxidation states of compounds, there are always some exemptions. And you will only be able to master this through constant practice. Let's solve the next example. We have FeCl2 plus K2Cr2O7 plus 14HCl yields FeCl3 plus 2CrCl3 plus 7H2O plus 2KCl. This is a very long reaction, but there are some tricks that you can do in order to shorten our solution. First, let us consider iron, both in the reactant and in the product side. If you take a look at the reactant side, iron is in FeCl2. In the product side, it is in FeCl3. So we have the same cation, that is iron, and we also have the same anion, which is chlorine. The only difference is the subscript of chlorine. In this case, in the reactant, the subscript of chlorine is 2. On the product side, its subscript is 3. Solely based on that observation, we can already say that one of the elements with changing oxidation state is iron. Because on the reactant side, since the subscript of chlorine is 2, the oxidation state of iron in this case is positive 2. If you perform the reverse crisscross that we have performed earlier, because remember that chlorine as an anion has a charge of negative 1. On the product side, iron would have a charge of positive 3, and chlorine would still have negative 1. You can do that if your anion is a halogen, that is fluorine, chlorine, bromine, or iodine, because their charge is -1. So you look here, 2 becomes the charge of iron, 3 becomes the charge of iron. So we now know that iron is part of one of our half reactions. So let's already list that as 6 FeCl2 yields 6 FeCl3. From +2, it became +3. Next, let us look for another element that changed its oxidation state. So what we can definitely say at this point is it is not chlorine, because if you take a look at the reactant and the product, chlorine stayed at -1. And in fact, we have here HCl, and from our previous example, hydrogen here is +1 and chlorine is -1. For KCl, potassium is +1 because it's a group 1 metal, and chlorine is again -1. So there is no change in oxidation state of chlorine. Now let's take a look at K2Cr2O7 in our reactant side. We know that potassium is a group 1 element, therefore its charge has to be +1 because it's our cation in this case. And we know oxygen to almost always have a charge of -2. And then we have here a middle element, just like in our previous example, and that is chromium. And what do we do with middle elements? We represent their oxidation state as X, and then we perform algebra to solve for the value of X. Let's do that here. For potassium, we have 2 times +1 because you have 2 atoms of potassium, plus 2 times X because you have 2 atoms of chromium, plus 7 times -2 for the 7 atoms of oxygen. And that is all equal to 0 because potassium dichromate is a neutral compound. Solving for X, we have here 2X is equal to 12. Therefore, X is +6. The charge of chromium in potassium chromates is +6. Now let's take a look at CrCl3 on the product side. Again, we know that chlorine as an anion has a charge of -1. And if you perform the reverse crisscross here, the subscript of chlorine, which is 3, would simply be the charge of chromium. And chromium being our cation would have a charge of +3. And then lastly, we have water. So you already know that the hydrogen in water has a charge of +1 and oxygen has a charge of -2. Therefore, what is the other element that changed its oxidation state? That is chromium. From +6, it decreased to +3. So we write as our second half reaction, K2Cr2O7 yields CrCl3. From +6, it decreased to +3. And since the oxidation state of chromium decreased, we say that that half reaction is the reduction, while for iron, it increased from +2 to +3. That is our oxidation half reaction. Okay, and we also say that FeCl2 is our reducing agent, and then potassium dichromate is our oxidizing agent. And with that, we have solved the problem. Let's take a look at the next one. We have copper plus nitric acid, HNO3, plus HBr yields copper bromide plus 2NO2 plus 2H2O. I will be leaving number 3 for you to practice, but I will help you in that copper here is a free element, and you know that free elements has an oxidation state of 0. Bromine in this case functions in the same way as chlorine in that it has a charge of -1 as well. Okay? The only thing new here is nitrogen. If nitrogen appears as part of a covalent compound such as in NO2, nitrogen has a charge of +4. But if nitrogen appears as the anion, nitrogen would have a charge of -3. Okay? In the case of HNO3, you would have to apply algebra again to solve for the charge of the middle element, which is nitrogen. Try answering this item, and if you want to know if you're correct or not, you can message me for confirmation. Let's proceed to balancing redox reactions. Redox reactions need to be written as half-cell reactions first before they can be balanced. That's why we started our lesson by determining the half-cell reactions of redox reactions. I will be showing you how to balance redox reactions by solving the following examples. By the way, we have two types of media and therefore two types of approach in balancing redox reactions. The first is in acidic media and the second is in basic media. So let's start with acidic media. Let's have number one. We have MnO2 plus Cl minus yields Mn2 plus Cl2. Here we have our unbalanced redox reaction. Now, we already know that this is a redox reaction just by looking at the oxidation states of chlorine. On the reactant side, its oxidation state is -1 because it is present as a chloride ion, while in the product side, its oxidation state is 0 because it's a free element. Okay? Now we need to separate this in its half reactions. Of course, the first half reaction would involve manganese, that is MnO2 yields Mn2 plus, while the second half reaction would include chlorine. That would be Cl minus yields Cl2. Now we have previously mentioned that the charge of chlorine on the reactant side is -1, while the elemental chlorine is 0. How about for manganese? For the manganese on the product side, its oxidation state is +2 because it's present as a lone cation, while on the reactant side, we have to solve for it. We know that the oxidation state of oxygen in this case is -2, but we do not know that of the manganese. So let us represent it as x, and then let's perform algebra to solve for the value of x. That would be x plus 2 times -2 is equal to 0. Therefore, x is equal to +4. We now know that the oxidation state of manganese in the reactant side is +4. Now, judging by the increase or decrease in oxidation states of the elements, we can judge if they are undergoing oxidation or reduction. Let's start with the manganese. From +4, it went down to +2. Therefore, this is a reduction half reaction. No? It gained electrons. That's why its charge became more negative. While for the second half reaction, it has to be oxidation because it's always paired with reduction. But if you take a look at the oxidation states, from -1, it increased to 0. So this is our oxidation reaction. Now, the next part is the balancing part. How do we balance these types of reaction? If you take a look at the reduction half reaction, you would notice that manganese is already balanced because we have one atom of manganese. Because we have one atom of manganese each on the reactant and the product side. However, you can see that there is oxygen on the reactant side, but there is no oxygen on the product side. So the problem is, how do we balance that part? Okay? The basic principle in balancing of redox reactions is you have to do the balancing in two parts. The first part is you first balance the mass or you balance the number of atoms. And the second part is you balance the charges on the reactants and on the product side. Let's start by balancing the number of atoms. If you take a look at our reduction half reaction, you would see that there are 2 atoms of oxygen on the reactant side, but there are none on the product side. For that, we have to add oxygen on our product side. But you cannot add just oxygen. If you want to add oxygen, you need to add water or H2O. Since we have 2 oxygen on the reactant side, we need to have 2 oxygen on the product side. Therefore, I will be adding 2 molecules of water. By doing so, we have already balanced manganese and oxygen. However, by the introduction of water, we also introduced hydrogen on the product side. So what we will do is we need to add hydrogen on the reactant side so that hydrogen will be balanced. So for acidic media, whenever you need to add hydrogen in your half reactions, you don't add H2, you simply add a proton or H+. In our case, we need 4 atoms of hydrogen in the reactant side to balance the equation. Therefore, on the reactant side, we add 4 H+. Okay? Always remember, if you need to add oxygen, you have to add water or H2O. And if you need to add hydrogen, you need to add the proton or H+. Okay? Now, let's see if the masses are already balanced for the first half reaction. Manganese is balanced, 1:1. Oxygen is balanced, that is 2:2. And hydrogen is balanced, that is 4:4. With that, we are done on the first part of the balancing. For the second part, we need to balance the charges on the half reaction. And by balancing the charges, that is as simple as counting the positive and the negative charges on the reactants and on the product side and ensuring that the summation of charges are equal. So for that, let's try to count the charges. For the reactant side, 4H plus has a total charge of +4, that is 4 times +1. MnO2 is a neutral compound, its charge is 0. Manganese 2 plus has a total charge of +2. And H2O is a neutral compound, therefore its charge is 0. Okay, so now we see that there is a total of positive 4 charge on the reactant and a total of positive 2 charge on the product side. Now for the balancing, we need to add electrons on the side that has too much positive charge. Remember that if you want to balance the charges, you can only add electrons, and electrons only contain negative charges. In this case, if I have positive 4 on the reactant side and positive 2 on the product side, I can add 2 electrons on the reactant side, such that if I add a minus 2 charge on the reactants, both the reactants and the products would now have a positive 2 charge. That is, 4 minus 2 is equal to 2. And with that, we have already balanced our reduction half reaction. Let's do the same for the second half reaction. We have Cl minus yields Cl2. Let's first balance the mass. We need to balance the number of chlorine atoms. On the reactant side, you have 1. On the product side, you have 2. So we simply multiply Cl minus by 2. There are no oxygen, there are no hydrogens, so this equation is already done with the mass balance. The next would be charge balance. On the reactant side, we have a total of minus 2 charge, that is 2 times negative 1. On the product side, our total charge is 0. Since we can only add electrons, I need to bring 0 down to negative 2, and that is simply by adding 2 electrons on the product side, such that negative 2 is equal to 0 plus negative 2. This is now a balanced half reaction as well. And once you have balanced the reduction and oxidation half reactions, the next thing that you have to do is to ensure that you have the same number of electrons on both half reactions. On the reduction half reaction, we have 2 electrons. On the oxidation reaction, we have 2 electrons as well. So this is already okay. Since the number of electrons are already equal, we can now proceed to add the 2 half reactions to have our balanced redox reaction. Now we can add. So the first thing that you should notice is that the number of electrons would cancel because they are equal. One is in the reactant side, the other is in the product side. And then everything else can be added down. So on the reactant side, we have MnO2 plus 2Cl minus plus 4H plus. On the product side, we have Mn2 plus Cl2 plus 2H2O. This is our balanced redox reaction. Now, if you want to make sure, you can perform a manual count of the mass and of the charges. Let's count the manganese. You have 1 in the reactant, 1 in the product. Let's count chlorine. You have 2 in the reactant, 2 in the products. Hydrogen, that is 4:4. And oxygen, that is 2:2. Now, for the total charge, MnO2 is 0. 2Cl minus is negative 2. 4H plus is positive 4. The total charge on the reactant side is positive 2. On the product side, Mn2 plus is positive 2. Cl2 is a free element, therefore it's 0. And then H2O is a neutral compound, therefore it's 0. Total charge on the product is also positive 2. Therefore, a correctly balanced redox reaction has to satisfy the balance of both the mass in terms of the number of atoms and the total charge. Okay? That is how we balance a redox reaction. Let's have the next example. We have FeS plus NO3 minus yields NO plus SO4 2 minus plus Fe2 plus. Let's first determine the oxidation states of the elements we have here. Let's start with FeS. Now, sulfur here is part of the anion and sulfur is part of group 6 along with oxygen. Therefore, it would have a charge of negative 2. And based on the subscripts of iron and sulfur on FeS, whatever is the charge of sulfur should also be the charge of iron. So iron here is positive 2. Now let's go to nitrate or NO3 negative 1. Oxygen has a charge of negative 2. We don't know the charge of nitrogen in this case, so let's have it as X and then let's perform algebra. So this becomes X plus 2 times negative 3 is equal to negative 1. The overall charge of the entire nitrate ion is negative 1. Okay? Solving for X, we have positive 5. So the charge of N in nitrate is positive 5. Okay? Next, NO. Oxygen here is still negative 2. And for the charges to balance, nitrogen should be in positive 2. Next is sulfates. Oxygen is negative 2. The overall charge of sulfate is -2. If you don't know the charge of sulfur, you let it as X. Therefore, we have X plus 4 times -2 is equal to -2. The charge of sulfur here is +6. And lastly, we have iron. The charge is already given, that is +2. So what are our two elements that experience a change in oxidation states? That is nitrogen. From +5, it became +2. And the next is sulfur. From -2, it became +6. Let's start with nitrogen. So we write NO3 negative yields NO, wherein the nitrogen in nitrate is at +5 and the nitrogen in NO is at +2. Next, we have sulfur. On the reactant side, sulfur is in FeS, and on the product side, it is in SO4 2-, but I will be adding Fe2+ as part of the products. Now, you might be asking why. Iron in this case is called a spectator ion because as you can see, it's not changing its oxidation state, but it is vital in the half reaction of sulfur. So that's why we are still including iron in the second half reaction. And besides, you have to include iron because you cannot balance the reaction without the iron in the product. Sulfur in the reactant side has a -2 charge, while sulfur in the product has a +6 charge. Now, our top half reaction experience a decrease in oxidation state from +5 to +2. So therefore, this is a reduction half reaction, wherein sulfur in our second half reaction experience an increase in oxidation states from -2 to +6. So this becomes an oxidation reaction. Now it's time to balance. Let us start with the reduction half reaction. Nitrogen is already balanced, one in the reactant and then one in the products. We just have to balance our oxygen. You have 3 in the reactant side and you only have 1 in the product side. Therefore, I need to add 2 oxygen in the product side. And since we don't simply add oxygen, we add water, I need to add 2 molecules of water in the product side to balance the oxygen. Since we have introduced hydrogen to our equation, I need to counterbalance that on the reactant side. We need to add 4H+. Now, nitrogen is already balanced. Oxygen is already balanced and hydrogen is also balanced. Next, we need to balance the charges. From the reactant side, we have +4 coming from 4 times +1, and then coming from nitrate, we have a total of -1. The total charge on the reactant side is +3. On the product side, the total charge is 0 because both NO and H2O are neutral compounds. So how can we balance the charges? We simply add 3 electrons on the reactant side such that +4 minus 1 minus 3 is 0. And that is in balance with the charges of the products. Okay, we are done with our reduction reaction. Let's proceed with the oxidation reaction. For the mass balance, iron is already balanced. We have 1 in the reactant, 1 in the product. Sulfur is also balanced, that's 1:1. But we have an excess of oxygen on the product side. To balance that, we add 4 molecules of water in the reactant side. That gives us 4 additional oxygen. Okay? And since we have introduced 8 hydrogen on the reactant side, we need to add 8 hydrogen in the form of protons on the product side. This equation is now balanced in terms of mass. Let's now balance in terms of the charges. On the reactant side, our total charge is 0 because water and FeS are both neutral compounds. On the product side, sulfate gives us -2 as the charge. Iron 2+ gives us +2 as the charge. While for our protons, that would be 8 times +1, that is +8. The total charge in the product side is +8. So we need to balance +8s in the product against 0 in the reactant. So for that, we need to add 8 electrons on the product side such that the total charge on the product side would be 0 as well. Okay? And that is a balanced oxidation reaction. Now, before we add, we need to make sure that the number of electrons are the same in the reduction and in the oxidation reactions. We have 3 electrons in the reduction and we have 8 electrons in the oxidation. And one way to make them equal is to multiply the first equation by 8 and to multiply the second equation by 3 such that we get 24 electrons both on the reduction and the oxidation sides. So let's multiply the first equation by 8. Let's multiply the second equation by 3. And then we can add. Electrons cancel because you have 24 on the reactants and 24 on the products. All of the remaining terms will be 8 nitrate plus 3 FeS plus 32 H plus 12 H2O. On the product side, we have 8 NO plus 3 SO4 2 minus plus 3 Fe2 plus 16 H2O plus 24 H plus. Now we can further simplify this equation by cancelling some of the excess H plus and H2O. On the reactant side, we have 32 H plus. On the product side, we have 24 H plus. If you subtract that, that is 8. Therefore, we only retain 8 H plus in the reactant side and then erase the one on the product side. Okay? We do the same for water. You have 12 water on the reactant side and then 16 water on the product side. The difference is 4, and there are more water on the product side. Therefore, we only retain 4 water on the product side and then remove the water on the reactant side. This is now our balanced redox reaction. If you want to make sure we can do a count of all of the atoms, let's do nitrogen. We have 8 on the reactant. We also have 8 on the products. For iron, we have 3 in the reactant. We also have 3 in the products. For sulfur, we have 3 in the reactant, and we also have 3 in the products. And lastly, for oxygen, this is 8, 16, 24 in the reactants. And in the product, you have 8 plus 12, that is 20, plus 4, you also have 24. Therefore, we have satisfied the mass balance criteria. How about the charges? For the charge balance, on the reactant sides, we have negative 8 coming from NO3. We have 0 from FeS, and then we have positive 8 from the H+. The total in the reactants is 0. On the product side, we have 0 from NO. We have 3 times negative 2 is negative 6 from the sulfates. And then we also have 3 times positive 2, that's positive 6 from the iron. And then we have 0 from the water. Total charge is 0. Therefore, our obtained redox reaction is balanced. Okay? Do not forget this technique. Let's proceed. For number 3, I want you to do this on your own. And if you want to know if you're correct or not, you can message me. Okay? Let's proceed. How about balancing redox reactions in basic media? Earlier, I have mentioned that we have 2 types of media, acidic and basic media, and their approach to balancing are quite different. For acidic media, we were adding protons to balance our half reactions. In this case, for basic media, we need to add the hydroxide ion instead. Okay? Let's try these examples. First, we have S2 minus plus Cl2 plus OH minus yields SO4 2 minus plus Cl minus plus H2O. Our initial approach in balancing this type of redox reactions is just the same as for that of the acidic media, but a key difference will just be added later. Okay? So let's first determine the oxidation states of the elements. For sulfur on the reactant side, we have negative 2. For the sulfur on the product side, we have positive 6 coming from the sulfate. This is just the same as the one we have solved earlier. For chlorine, it's 0 on the reactant side because it's a free element. On the product side, it's negative 1 because it's present as chloride. At this point, we don't even need to determine the oxidation states of oxygen and hydrogen because we now know that sulfur and chlorine are the 2 elements that change their oxidation states. Okay, so let's build the half reactions. Let's start with sulfur. On the reactant side, we have S2 minus. On the product side, we have SO4 2 minus. Next, we have Cl2 yields Cl minus as our next half reaction. So our first half reaction is an oxidation reaction because sulfur went from negative 2 to positive 6. And our next half reaction is the reduction reaction because chlorine went from 0 to negative 1. You might be asking, why did I not include OH minus and H2O in our half reactions in this balancing? We don't need to include them because they will just appear later in our balanced equation. Okay? Let me show you how. So for the first steps of the balancing, we will do this in such a way that it resembles the balancing of an acidic media. Okay? For the oxidation reaction, we balance the sulfur. It's already balanced. For oxygen, we have 4 in the product side, so we need to add 4 H2O on the reactant side to balance the oxygen. And since we have introduced 8 atoms of hydrogen, we add in the product side 8 H+. Now, here comes the part that distinguishes basic media from acidic media. At this point, you need to add hydroxide ions on both sides of the equation that is equal to the number of H+ ions in your reaction. So in the product side, we have 8 H+. Therefore, we need to add 8 OH- on both sides of the reaction. And a very important side note here is when you add a hydronium ion or an H+ ion with a hydroxide ion or OH ion, you simply get water or H2O. So in this case, we have 8 hydronium plus 8 hydroxides. This would just give us 8 molecules of H2O on the product side. Okay? And since you have water on the products and water on the reactant side, we can cancel some of the excess water. So let us simplify our half reaction. On the product side, we now have 8 H2O. But since we have 4 H2O on the reactant side, I can erase that and then transfer that to the water on the product side. Therefore, on the product side, we only have 4 H2O. Okay? So tidying this up, we now have 8 OH minus plus S2 minus yields SO42 minus plus 4 H2O. Now, let us check if this is still balanced in terms of mass. Oxygen, we have 8 on the reactant. On the product side, we have 4 plus 4 equals 8. Hydrogen, we have 8 on the reactant side. We also have 8 on the product side. And sulfur still remains as 1:1. So this reaction is still balanced in terms of mass, but now it is balanced as a basic media because instead of the H+ or the hydronium ion, we have the OH- or the hydroxide ion. Okay? What's left for us is to balance the charge. So balancing the charges, we have -8 from OH. We have -2 coming from sulfur. The total charge on the reactant side is -10. And the total charge in the product side is -2 plus 0. That is -2. To balance, we need to add 8 electrons on the product side such that -2 minus 8 is equal to -10 on both sides of the equation. That is how you balance half reactions in basic media. Let's do the same for the second half reaction. For our reduction reaction, the balancing is simply you multiply Cl- with 2 to balance the number of chlorine atoms. And then to balance the charge, we simply add 2 electrons on the reactant side. Now, before we can add, we need to make sure that the number of atoms in the oxidation and reduction half reactions are the same. So seeing that we have 8 electrons in the oxidation and only 2 electrons in the reduction, it is fitting that we multiply our reduction reaction by 4 to ensure that we also have 8 electrons. Adding the two equations, electrons cancel. So we have S2 minus plus 4 Cl2 plus 8 OH minus yields SO4 2 minus plus 8 Cl minus plus 4 H2O. Let's check if it's still balanced in terms of mass and charge. In terms of mass, sulfur is balanced 1:1. Chlorine is balanced, that is 8:8. Oxygen is also 8:8. And hydrogen is also 8:8. So the masses are balanced. In terms of charges, on the reactant side, we have -2 plus 0 minus 8, total -10. On the product side, we have -2 plus -8 plus 0, total is also -10. So our mass and charge are both balanced. Okay? That is the basic principle for balancing in basic media. Let's do the next example. We have N2O4 plus Br2 yields NO3 minus plus Br minus. For this example, since we have 2 reactants and 2 products, we are certain that all of this would figure out into our half reactions. Okay? Our first half cell reaction will concern nitrogen. So we write N2O4 yields NO3 negative. And of course, our second half cell reaction will become Br2 yields Br negative. Now, if you want to take a look at the oxidation states of all of the elements here, we can. For bromine, this is 0 because it's a free element. For Br minus, it's -1 because it's the anion bromide. For nitrogen in N2O4, if you perform the reverse crisscross, you would see that oxygen is at a -2, while nitrogen is at a +4. And for the nitrogen in nitrate, if you perform a little side calculation here, if oxygen is -2 and nitrogen is represented as X, we write the equation as X plus 3 times -2 is equal to -1 because the overall charge of nitrate is -1. Okay? And solving this equation, we get that X is +5, or the oxidation state of nitrogen in nitrate is +5. So now we know that our first half reaction is our oxidation reaction because the oxidation state of nitrogen increased, while our second half reaction is our reduction reaction. Now let's try to balance the first half reaction. Let's begin by balancing the number of nitrogen atoms. So you have 2 nitrogen on the reactants. On the product, you only have 1. And to balance nitrogen, we multiply nitrates by 2. Next, we balance our oxygen. On the reactant side, we have 4. On the product side, we have 6. So therefore, we need 2 oxygen on the reactant side, but we add water. So we add 2 molecules of water to balance oxygen. And finally, to balance our added hydrogen, we need to add 4H plus on the product side. Okay? Until this point, this is still balancing in acidic media. To make it balancing in basic media, we add hydroxide ions. So you have 4 hydronium or H plus ions on the product side. So we need to add 4 hydroxide as well to both sides of the equation. What that does is 4H plus 4OH becomes 4H2O. And then you have 2H2O on the reactant side, 4H2O on the product side. This can be transposed and subtracted from 4, giving us 2H2O. Okay? So our balance reaction is now 4OH minus plus N2O4 yields 2NO3 minus plus 2H2O. Next, balancing the charges, we have -4 from OH, 0 from N2O4, -2 from NO3, and then 0 from H2O. So that is -4 total on the reactant side and -2 total on the product side. To balance things out, we need to add 2 electrons on the product side. Next half reaction, there are no oxygen nor hydrogens, so we simply have to balance the number of bromine. So there are 2 bromine on the reactants. On the product, you simply multiply it by 2. Now to balance the charges, bromine has 0 charge on the reactants. On the product side, it's -2. That is 2 times -1. Therefore, we need to add 2 electrons on the reactant side to balance the equation. Okay? And then take a look at the number of electrons. You have 2 in the oxidation and also 2 in the reduction. It's equal. Therefore, we can already add this reaction. Electrons cancel. And we are left with N2O4 plus Br2 plus 4OH minus yields 2NO3 minus plus 2Br minus plus 2H2O. This is now our balanced redox reaction. To check, let's perform a mass and charge balance. For the masses, nitrogen, you have 2 on both sides. Oxygen, you have 4 plus 4, 8 on the reactant side. On the product side, you have 6 plus 2 is equal to 8. That's also balanced. For the bromine, that's 2:2, balanced. And for hydrogen, we have 4 in the reactant side and 4 in the product side as well. For the masses, you have 0 plus 0 minus 4. That should be equal to -2 minus 2, 0. So -4 total is equal to -4 total. This is now our final balanced equation. Okay, so the only difference between balancing of acidic and basic media is that in acidic media, you should be left with H plus in your balanced reaction, while for the basic media, you should be left with OH minus in the balanced reaction. Okay, let's go back. This last example, HS minus plus ClO3 minus yields S plus Cl minus, will be left to you as a practice problem. Okay? So if you want to improve in balancing of redox reactions, you need to keep on practicing with both acidic and basic media. The skill of balancing redox reactions will be carried over when we are already discussing electrochemistry proper. All of this discussion about redox reactions is just an introduction to electrochemistry proper. Okay, so this has been part 1 of the lecture. Please proceed to part 2, in which we will already discuss electrochemistry proper along with its applications. Thank you and keep safe.